All right, welcome to the Explainer. Today, we're setting the stage for an absolute masterclass in extreme engineering. We are looking deep into the mechanics of drilling rigs, a place where failure isn't just an inconvenience, it's catastrophic. But here's the really fascinating part. Engineers don't just build these massive structures, crossing their fingers and hoping they won't fail. They actually anticipate that failure. They design for it. So today, we're going to explore exactly how they outsmart destruction.
So, here's our roadmap for this explainer. 1. Designing for destruction. 2. The language of pressure. 3. Sealing the underground. 4. The last resort. And finally, 5. The human hazard.
Okay, let's dive straight into Section 1, Designing for Destruction, Anticipating Mechanical Wear.
There's this huge misconception out there that engineers try to make everything on a rig totally unbreakable. But they don't. That's practically impossible when you're literally grinding thousands of feet of solid steel into rock, right? Instead, they make a highly calculated decision about exactly what breaks and exactly when by following one golden rule: wear out the cheap part, not the expensive one. We call this wear budgeting. See, every single cycle of machinery, every time you make and break a connection, it damages the metal just a tiny amount. Those cycles have to land somewhere. So engineers purposefully put a cheap, easily replaceable component directly in the load path just to absorb that punishment.
Just look at this comparison to see what I mean. On one side, you've got a $25,000 Kelly. It's this massive, precision machine piece of steel. And on the other, a $1,500 Sabre sub. If you screw the drill string directly into the Kelly, say 500 times a well, you are going to absolutely destroy the Kelly's threads. Instead, you attach that cheap Sabre sub once and let it take all the daily destruction. It's exactly like slapping a cheap plastic screen protector on a $1,000 smartphone. It takes all the scratches so the expensive hardware beneath stays pristine.
And once you kind of wrap your head around that concept, you start seeing this sacrificial pattern absolutely everywhere on the rig. Bit subs exist purely to take the wear instead of the super expensive drill collars. Wear bushings just sit in the wellhead so the drill string chews on them instead of tearing up the precision sealing surfaces. Even bumper blocks, they work specifically because they crush to absorb a catastrophic impact. A rigid steel stop would just snap the line instead. All of these parts exist to be destroyed on purpose.
Moving right along to Section 2, the language of pressure, decoding invisible forces. Okay, so a drilling crew works with these immense, highly pressurized forces that they can't even see. To survive out there, they basically have to learn to fluently read the language of pressure. I want you to test yourself real quick with this real-world scenario. Your standpipe pressure has quietly dropped by 150 psi. The pump rate hasn't changed. Nothing else looks different at all. What do? Well, a gradual, unexplained pressure drop is drill string language for a leak. It means fluid is escaping somewhere it absolutely shouldn't be. And if you ignore it, you are on a fast track to disaster.
Here is how fast that failure progresses. It always starts with an under-torqued connection. That leads to a loose shoulder. Then, that high-pressure mud starts jetting through that tiny little gap, eroding the hardened steel in a matter of hours. We call that a washout. If you ignore that 150 psi pressure drop, that washout just cuts right through the metal until the drill string literally parts and snaps in half, leaving all of your extremely expensive tools abandoned at the bottom of the well.
Now this brings up a really fascinating misconception we need to clear up. Most people just assume the threads of a pipe create the pressure seal, kind of like a garden hose. They don't. Rotary connections actually seal on the flat shoulder faces that slam together when you torque them up. The threads? They only exist to pull those two shoulders into tight contact. If the shoulder doesn't seal tight, the mud jets out and the connection washes out. Simple as that.
And because that flat shoulder is the seal, applying torque can never, ever be a guess. It always comes straight from the API chart, never from feel. Actually, let me put it this way. If an operator relies on a stalled tool's feel to decide if a connection is tight, it guarantees a washout. That is exactly why modern automated systems like the Iron Roughneck apply and measure torque so accurately. Makeup is a hard recorded number, not a feeling.
Which brings us to Section 3, Sealing the Underground, Managing Downhole Traps.
So we've talked about how connections hold pressure up top, but how do we manage pressure traps much deeper in the earth? How do we block or direct immense pressures thousands of feet below the surface? Well, there is a fundamental difference between the two crucial sealing devices used downhole. A packer isolates a section of the annulus, sure, but it keeps a flow path open straight through its center bore so production fluid can still pass. A bridge plug, on the other hand, blocks absolutely everything. It is a solid stop. That's the whole difference between the two.
Now, whether you're using a packer or a bridge plug, the way they actually set is pretty genius. It's always anchor first, then seal. These tapered metal teeth, called slips, bite outward to anchor into the casing, and only then does the rubber element get squeezed to form the actual seal. But here's the catch. Those slips absolutely need sound casing to bite into. If you try to set a critical plug inside corroded or heavily worn casing, those teeth just won't get a proper bite. The plug might hold fine during a quick test, but it's going to slide right up the hole under real sustained pressure.
And that leads us to a really hidden danger. A sealed annulus is not inherently a safe annulus. Think about it. If you trap fluid between two seals downhole, the geothermal heat of the earth naturally warms that trapped fluid. And since liquids essentially cannot compress, the pressure inside that closed loop rises incredibly fast. Engineers have to constantly monitor closed spaces because a trapped volume that heats up can literally burst the casing from the inside out.
All right, Section 4, the last resort, blowout prevention and redundancy.
Let's escalate the stakes a bit here. What happens when the pressure actually overwhelms the mud weight? We have to move to the absolute ultimate defense against disaster. Because remember, no single seal holds a well. The BOP stack, or blowout preventer, uses what we can call aviation redundancy. Just like a commercial airliner doesn't rely on a single hydraulic system, a BOP stack is this massive tower of layered, completely independent barriers. You've got an annular preventer that seals around anything, and then pipe rams tailored to specific pipe sizes beneath it. Plus, the redundancy totally extends to the controls. The driller's console, a remote escape panel, and the accumulator unit itself can all independently slam that well shut if things go south. So, how do you actually guarantee that this giant layered beast is going to work when you need it most? 21. That is the API rule. You absolutely must pressure test the BOP stack at intervals not exceeding 21 days. And crucially, you always do a low pressure test first, usually around 250 to 350 psi. Why? Because high pressure actually energizes rubber seals and forces them to grip. If a seal is failing, it might somehow hold 10,000 pounds of pressure but leak at 200. The low pressure test proves the rubber seals entirely on its own merit without being over-energized.
I think this quote right here really drives home the gritty reality of extreme engineering. Safety equipment sitting idle for weeks proves absolutely nothing until it is tested. An untested BOP that hasn't been rigorously verified, it's just a confident guess. It is an assumption, not a barrier.
And then, at the very bottom of that whole BOP stack, you have the shear rams. Look, shearing works. It's essentially two massive steel blades that will cut clean through the heavy drill pipe and seal the open hole to save the rig. But it costs you the drill string in the process. It drops thousands of feet of pipe straight to the bottom of the well. It is a highly effective, multi-million-dollar sacrifice, which makes it the ultimate last resort, not your first move.
And finally, Section 5, the human hazard, when operators overrule engineering.
We've spent this time talking about structural sacrifices and blowout preventers, but honestly, the most unpredictable variable on any rig isn't the rock and it's not the pressure. It's us. It's human behavior and the incredibly dangerous temptation of the shortcut. Take a crown out, for example. That's when the massive traveling block is accidentally hoisted completely up into the top of the derrick, utterly destroying the rig. Now, there is an automatic toggle switch called the crown-o-matic, designed to stop exactly this from happening. Yet pretty much every single crown-out investigation finds the exact same tragic thing. The safety device was deliberately bypassed by a human simply to save a little time during fast tripping.
Human error just completely compounds the danger out there. A cathead winch operates on friction, right? Slipping is actually the safety feature that keeps you from being pulled in. Yet operators constantly override it by taking extra wraps or literally wrapping the rope around their hands, causing terrible, fatal accidents. Or consider the rig's friction brakes. If a crew decides to mix thick and thin brake friction blocks just to save a few bucks, all the intense heat concentrates on those few thick blocks. Those super hot brakes fade and grip way less. And here's the scary part. Brake fade gives absolutely no warning through the driller's lever until it is way too late. The engineering was perfectly sound. The human shortcut is what caused the hazard.
And I think that brilliantly illustrates our final takeaway for today. We've spent this entire explainer looking at the extreme, high-stakes environment of a drilling rig, but honestly, this logic applies everywhere. The most brilliantly engineered, hyper-redundant safety equipment in the world is completely 100% useless if a human decides to bypass it just to shave a few seconds off a job. So I want to leave you with this provocative thought. What is the casually defeated safety device in your industry?
Thanks so much for joining me on this explainer, and stay curious.